Hey, Phys 1 students, and welcome to our last topic of the semester. We're going to be talking about angular momentum, which is an extension of what we talked about with linear momentum or translational momentum. And it's another one of these really special quantities in nature that is conserved, which means that as far as we can tell in the universe, there's a certain amount of angular momentum that exists. It never gets created or destroyed. It only gets transferred from one system to another. But to fully appreciate what that means and all the cool things we can do as angular momentum gets transferred from one system to another, we first have to really rigorously define what angular momentum means. So just like we did with Newton's second law of translation, where we extended it to Newton's second law for rotation for things that can and do rotate, we're going to do that for momentum, extending it to angular momentum, and finding that it's useful even when something isn't really rotating. Just like with Newton's second law for rotation, we use that to solve a lot of statics problems, even though there wasn't anything rotating to begin with. So let's go over a couple quick definitions before we get started. So first, this capital L stands for angular momentum. Not sure why it's a capital L, maybe the lure in angular, I'm not really sure. But we have the particle definition, meaning if you have a particle translating, we're going to define the angular momentum there to be r cross p, where this is similar to torque, where we have to define a point or an axis about which we're calculating the angular momentum. So r goes from the axis to the place where the particle actually is. So if that particle is moving with a linear momentum p, then its angular momentum would be r cross p. If we have a collection of objects that are, collection of particles, that are making up an extended object, and they're all rotating together about some axis of symmetry. So let's say I have my cup here and I rotate it. We could talk about the angular momentum of my cup by taking the moment of inertia of the cup and multiplying it by its angular velocity vector, where I would use the right-hand rule to say if my cup is rotating this way, such that the fingers of my right hand curl in that direction, the angular velocity or angular momentum would point in the direction of my thumb. And then we are also going to define the angular impulse momentum theorem, where if I know the impulse acting on my system due to external torques, as opposed to forces in this case, we're going to be talking about torques, then that will change the angular momentum of my system. And then lastly, we can also talk about the rotational kinetic energy of something that has angular momentum. And we know that rotational kinetic energy is 1/2 I omega squared. But if we use the magnitude of the angular momentum for an extended object, we can see that we could also write this as the angular momentum squared divided by 2 times the moment of inertia. This should remind you of what we did with linear momentum and translational kinetic energy, where we could write it as 1/2 mv squared or p squared over 2m. All right, let's get some practice with this though. So first, to warm up, we want you to think about which of these following statements about angular momentum for a translating point mass is false. So A, the angular momentum of a point mass depends on your choice of axis. B, the angular momentum of a point mass depends in part on the linear momentum of that point mass. Or C, since the point mass is purely translating, it has no angular momentum. So we're going to give you a few minutes to think about this while you switch to the next video.